Welcome to Flux Electrical channel. Like, comment and subscribe to the channel to get notified whenever a video like this is being posted next time. Today let's talk about a very important factor in electrical engineering, which is power factor in power system. This is a very crucial tutorial that every electrical engineer and student cannot afford to miss. Try and watch till the end of the video. Before I start, it is important to know that the term power factor is only occur in alternating current systems, not direct current circuit. The reason is that direct current systems, the phase angle between current and voltage is zero. This means that current and voltage are in phase or steps. So let's continue with the topic of the day. What is power factor? Power factor (PF) is a measure of how effectively electrical power is being converted into useful work output. It is measure of useful power in the electrical system. This implies that not all the powers in electrical system are converted to useful work. It indicates that others are being used by the circuit itself. For not utilizing all the power to useful power, the optimal performance of the system cannot be achieved. For proper and easier understanding of what power factor is, let's use a glass of beer that is mixed with foam as an analogy as shown below. In this case, the consumer buy beer with the aim of satisfying himself and finishing all the beer in the glass. Unfortunately, while putting the beer in a glass, it forms a mixture of beer and foam. Some beer is converted to foam, which reduce the quantity of beer in the glass. At the end of the day, he became unsatisfied because he didn't got equivalent of what he paid for, because some part of the beer converted to foam which is unconsumed. From this analogy, the beer plus foam in the glass represents apparent power of the system, which is the total power. The foam at the top of the glass represents the reactive power, which is power that does no useful output work, rather the power is being used to maintain the system. Lastly, the beer represents the real power, which is the useful output power that consumers use to power their homes. From this analogy we have understood that the higher the real power, the lower the reactive power in the system, thereby increasing the system efficiency. Then we called this improved power factor. But whenever the reactive power goes higher, the real power, which is the useful power, becomes lower, thereby decreasing the system efficiency. Then we called this poor power factor. Because of this, engineers design and construct electrical systems with high power factor and also incorporate some power factor improving devices into the system. Without improving this power factor, utility companies suffer losses whenever the power factor of the system is low, thereby making the utility companies to pay more on losses than in profit making and other damages it does to the system itself. But what actually do we mean by low power factor value, and what happens to voltage and current value in this state? At low power factor, current taken by the electrical systems is always high. For instance, electrical motor, it will draw higher current than before. At low power factor, the supplied voltage to the circuit remains relatively constant. It is important to know that power factor values ranges from 0 to 1. Watch my video on reactive power to understand what happened when power factor is 1 or less than 1. Let's proceed. Note that high power factor indicates that the current and voltage waveforms are closely in phase with each other. Let's discuss effects of low power factors. In every engineering designs and constructions, the sole aim is to reduce losses, reduce costs and improve systems performance optimally. Having low power factor is disadvantageous to the system performance. There are some significant effects which low power factor inflict on power system. These effects include the following. 1. Increased losses in the power system. Low power factor leads to higher currents for the same amount of real power delivered. This can increase resistive losses, I²R losses, in electrical conductors and transformers, leading to wasted energy and higher operational costs. 2. Poor voltage regulation. As current increases in the power lines due to low power factor, there is a greater voltage drop along the length of the wire before the receiving end. This can result in inefficient delivery of voltage to end users. 3. Higher electricity costs. Many utility companies impose penalties for customers with a low power factor. This results in higher electricity bills, shifting the cost burden to the user. 4. Larger equipment. Electrical systems with a low power factor may require larger transformers, conductor sizes and generators to handle the increased apparent power, which translates to higher initial costs and increased maintenance. This is because power factor is inversely proportional to the apparent power measured in volts-amps. As the current increases due to poor power factor, the system will become larger to possess required current carrying capacity for the design, thereby making the size of the equipment larger. 5. Reduced efficiency. The overall efficiency of the system diminishes, meaning more energy is consumed without an equivalent output in work, leading to higher operational costs. 6. Reduced system reliability. Constant high currents can stress electrical equipment, causing breakdowns and requiring more frequent maintenance and replacement, leading to outages and interruptions, reducing overall service quality. In summary, maintaining high power factor is crucial for optimal efficiency, cost management, and the reliability of power systems. Thank you for your time and energy. If this video is helpful to you, like, comment and subscribe to the channel to get notified when I post a video like this.